Well, hello, my beloved friends. It looks like that we near the end of the journey, and I know that you're all disappointed, having put in so much time dealing with parametric statistics and working with normal curves, that now we should journey into the world of non-parametric statistics. You've done well to make it so far, Pilgrim, and to keep so much hair with so many after it. For those of you that have seen the movie Jeremiah Johnson, we shall move into this lesson. Well, I guess it behooves us at this point to ask the question, do you remember the normal distribution curve? A normal distribution curve is a beautiful thing, and one could almost wish that that's all that there was. You could master the normal distribution curve and life would be wonderful and hunky-dory and wonderful. There are a lot of things that are normally distributed. There might be something that's not. Well, we start out. Let's look at some things that are assumed to be normally distributed. Don't you love reading about galaxies? You go out at night and you look into the size and then the stars, and you think they're stars and they're in fact entire galaxies. The sizes of galaxies appear to be normally distributed. The weights of stars appear to be normally distributed. The heights of people appear to be normally distributed. Some argue that intelligence is normally distributed. Nose links, ear links, and all sorts of things, and the size of our large feet may be normally distributed. Chickens are normally distributed in weight. Chickens are normally distributed in heights. Chicken running speed is normally distributed. That's cool. I love starfish. You go to the ocean and you find them, and the size of starfish is normally distributed. Oh, and my favorite creatures, aardvarks. Aardvarks by weight are normally distributed. Banded aardvarks have a band width which is normally distributed. Hungarian banded aardvarks are normally distributed in the size of their ears, and the albino Hungarian banded aardvark is normally distributed in the length of its nose. So many things are normally distributed. Don't you wish everything was normally distributed? Well, before you answer whether you wish everything was normally distributed, would you want the grades in this course to be normally distributed? I remember that I had a teacher one time that came into class, and it was a large class, and he said the grades in this course will be normally distributed. And he proceeded to tell us what that meant, and I rapidly decided that I didn't want my grades normally distributed. Consider the following. If grades were normally distributed, then that means that we would have 2% A's and 2% F's. We would have 14% B's, 14% D's, and we would have 68% C's. How would you guys like that? Wouldn't that be fun? It would be so much fun because in this course only 2% of 20 is 0.4, so I'd round that down to 0. I'd give no A's. Of course, I'd give no F's. I'd give 3 B's, 3 D's, and 14 of you would make a C. We love normal distributions, don't we? Well, thank goodness. Some things are not normally distributed. Some are not centered with their mass in direct center of the curve like is the normal distribution curve, but some things are skewed to either the left or skewed to the right with their distributions. Consider this beautiful little curve. Do you notice that over to the left there's a mass of the population, and then as it tapers off going to the right, fewer and fewer reach over there. This distribution is called a chi-square distribution, and it can be created by graphing the sample variance of a population of sample size n. Now, if we draw an infinite number of samples of size n, and we graph the variances of those samples, we would find a distribution which looks something like this. Now, what's interesting in this is that we can have a rejection region. And of course, now guys, keep in mind that you can have a two-tailed or one-tailed rejection region. Most of what we've been looking at is a one-tailed rejection region. It can be on either end with a given percentage. In this particular picture, I've selected a 5% rejection region, one-tailed off to the right, and everything to the left is accepted. This distribution is represented by the Greek letter chi, with a square on it. So chi-squared, it uses an F statistic to determine the significance or determine the rejection region. Now, these are things that are kind of fun. We'll work through them. Mainly, you're going to be reading a computer readout, which will give you a significance, which we will work in the next little PowerPoint to help you understand what that means. But I want you to know in this chi-square distribution, this is a one-tail test. On the left, you have all of that which is clear white under the curve. That's apparently a failure to reject region or acceptance region. Over to the right, we have 5% of the data which are rejected. Chi-square curves can take many forms. I thought these were pretty little pictures. In one of these, it's skewed to the left, and notice the one on the left, the rejection region is red. The one in the right, the data are skewed to the right, and the rejection region is on the right. The chi-square distribution consider rejection areas on each end. The curve certainly can be used for hypothesis testing. If you will notice in this diagram where it says area equals alpha over 2, you ought to recognize that those are rejection regions for H naught. And we might set a 0.05 alpha, which means we would have 0.025% on 0.025 rejection on each end. So we have a 2.5% rejection on each end and a total rejection of 5%. This is an example of a two-tail test in a chi-square curve. Now notice that the 2.5% over on the left differs in appearance from the 2.5% over on the right. That's because of the differences in the curve. So we would have different F values that would set the boundaries. There are some great and profound truths to be gained from the chi-square distribution. One of them is, of course, before we get into these two, is that grades are not normally distributed. When that teacher came in there and was going to normally distribute his grades, demonstrated his lack of understanding of statistical distributions. He apparently only had the first part of a little statistics class where all he had examined was the bell curve, and he went out on a rampage to force everything to fit a bell curve. Well, grades are not normally distributed. Grades are generally chi-square distributed, and they will cluster in the A, B, and C range and kind of taper off when you get into the D's and F's. Aren't you proud of that? Some of you are sitting there, oh, thank God, where some of us might get an A in here. Others of you are thinking, oh, at least we're going to get a B. Some may be happy with even less than that. But grades are chi-square distributed. Now, the interesting thing is we don't do a lot of statistical tests on grades. But how many of you are thinking about distributing a Likert scale survey out to be part of your dissertation? The Likert scale responses are not normally distributed. The Likert scale responses are generally chi-square distributed. So Likert data should be handled not with a normal distribution curve type of methodology, but instead they should be handled with non-parametric methodology. Now let that sink into you just a minute. How many times have you taken a survey and then later you read about, well, they did an ANOVA on it? Well, ANOVA is for normally distributed data. We're going to learn how to handle some of these things without doing normal distribution processes on them because they are not normally distributed. They are chi-square distributed. They are non-parametric. So if you have Likert scale data, they're not normally distributed, they're chi-square distributed, and then you're going to use some of these non-parametric processes on them. Isn't that interesting? I thought you would enjoy that. Have a good rest of the lesson. Live long and prosper, and watch out for the laws.